We have a couple problems here we're going to work on, and these are dealing with equilibriums. And if I have a set equilibrium here, such as hydrogen and iodine react to form HI, what's the equilibrium constant when we settle to a certain value? So this problem here has 2 moles of hydrogen and 2 moles of iodine mixed in an evacuated 1 liter vessel. Evacuated means there's nothing in it beforehand. And then 3.5 moles of HI are produced. So what we have to do in this type of question is we have things that are initial values. So something like the hydrogen and iodine are initial values. And then this here is an equilibrium value, which is what happens after the reaction settles to an equilibrium. So I have this information here. And the first step in any of this is you have to have concentrations of things, because the question asks for a Kc, which is the concentration equilibrium constant, and that involves molarities. So I have set up here, even though it's a 1 liter container, I still want to show that because it's not automatically going to be a 1 liter container. We divide it by 1. It could be a bigger or smaller container. So if I have 2 moles of H2 in 1 liter, well, that's 2 molar. Same with I2, also 2 molar, because they're the same. And this value here is not the initial, it's at equilibrium. So this is 3.5 molar, and we'll see where that fits into this equation here. When I look at a changing equilibrium, because we start off with initial values and we eventually get to equilibrium, we want to set up a table. And most often this is called an ice chart. I like to use a rice chart because I always like to write the reaction up here. So R is reaction, ICE, I is my initial, C is my change, E is my equilibrium. So initial values, if you have values, you're going to plug them in. And here I have 2 molar for my H2, 2 molar for my I2. And because it's evacuated, initially my HI is going to be 0. So I had no HI to begin with. But then as we change, these are going to go down. Okay, so this is going to drop. And because it's got no coefficient in front of it, we're just going to say it's going to drop by a value of X. Same with I2. These are the same proportions, so they're related to each other. This will also drop by X. Well, HI, this does not drop. It's going to increase because we're going to produce HI. But it's not going to increase by X. Because we have this coefficient here, it's going to go up by a factor of 2x. So these are related. Remember stoichiometry, it's a 2-to-1 ratio. So same here, so this is also going to be a 2-to-1 ratio. So this will end up being 2 minus x here. This is 2 minus x. This is 0 plus 2x, or just 2x. And now you're thinking, well, do we have some algebra we're going to do? Well, maybe a tiny bit, because I know that this right here is my equilibrium value, which is also what 2x is. Okay, so 3.5 molar is equal to 2x, which means x, if I divide by side 2, okay, x ends up being 1.75 molar. Okay. So now you have x. We know this is 3.5. We can actually go ahead and plug x into these up here. Okay, solve for x. I mean, we have x, we solve for the equilibrium values of H2 and I2. So H2 at equilibrium now is 2 minus 1.75, which ends up being 0.25. It's also what I2 is equal, so 0.25 molar, because these two are the same. And am I done? Well, close. I need to figure out what my Kc is. So Kc, remember my expression for Kc is going to be products over reactants raised to the powers. So Hi squared all over H2 times I2. This is all equilibrium values, so make sure we use the equilibrium values here. So my Hi is, careful, don't use the 1.75, we're going to use the 3.5 molar. And then on the bottom we have 0.25, and then 0.25, and then got a calculator. Go ahead and plug that in. I'm going to use this function here. You have that function on your calculator, that's really nice. So 3.5 squared divided by 0.25 times 0.25, and we got 196. Okay, so no units on the equilibrium constant. Question 2 is very similar. So when you do question 2 here, go ahead and do the same thing. Question 3, I changed it a little bit from your problem here. So this is H2 plus I2 goes the same equilibrium. I have 0.5 moles of H2, 0.5 moles of I2, same 1.0 liter vessel. I heat it up, and at the temperature, the moles of H2 decreases. This is the moles of H2 decreases to 0.19 moles. What's the equilibrium constant? So this is very similar. I'm going to have my molarities. So 0.5 molar here, 0.5 molar here for H2 and I2 initial. So I set up my Rice chart. And I have 0.5 molars for my initial 0. Gonna go down by x, go up by 2x. But now I don't have this value, but I do have H2, which says it went down to 0.19 moles, which in a 1 liter vessel, so I'll write it out, H2 at equilibrium, 0.19 moles over 1 liter to molarity, so it's 0.19 molar. So this is now 0.19 molar, okay? Which is also, I should write this out. So instead of writing that out here, I'm gonna write this out, 0.5 minus x. This is 0.5 minus x, and this is 2x. And we know that 0.5 minus x is equal to 0.19 molar. Okay, so from there, we can solve for x, and then we can do our x's and get our equilibrium constant. So you can do that one. The last question is also changed. I have this equilibrium here. NO gas goes to N2 plus O2. And I heat it up, it decomposes, so it breaks down. And it says, after the system has reached equilibrium, 57% of the original NO gas has decomposed. Determine the value of Kc for the reaction. So this one I'm starting with 0.5 moles of NO gas. and now 57% of it has decomposed. So how do I do that? Well, my initial NO is 0.5 moles in 1 liter, so it's 0.5 molar. But then at equilibrium, 57% of this is gone, which means I have 43% left, okay? So I want to get the equilibrium value, and you could do this either way. I like to just solve for the equilibrium value, so I know that 43% remains, so 57% decompose, 43% remain. So what is 43% of this value? Well, it's just going to be 0.43 times 0.5 molar. Okay, so 43% of 0.5 molar. And I do that, and that is 0.215 molar. So this value is going to go into the Rice chart. Somewhere. So when you set it up, and we have 0.5 molar here. It's an evacuated vessel, so these two should be at 0 to start. Then this is going to go down, and how much will it go down? Well, 2x, by a factor of 2x. This is going up by x. Go up by x. So I plug in my things here, carry them down, 0.5 minus 2x, x, and x. And where does this go? Well, this ends up being what this is right here. Okay, so I can set my 0.215 to be this expression, solve for x, and then you can do everything else. Okay, good luck.